Hey everyone, and welcome. Today we are diving headfirst into the absolute coldest corners of the known universe. I'm talking colder than deep space, colder than anything that exists in nature. We're going there to explore a truly bizarre state of matter, where the normal rules of reality seem to, well, bend, and thousands of individual atoms start acting like one.
So let's start with a big question. What actually happens when you get something as cold as it can possibly get? I don't just mean freezing. I mean getting so cold that you stop atoms almost completely in their tracks. And the answer? Well, it's not just some super frozen ice cube. It's something else entirely. Something that was predicted long before we could ever hope to create it.
Okay, so you remember from school, right? The basic states of matter: solids, liquids, and gases. You heat up a solid, it melts into a liquid. Heat up the liquid, it turns into a gas. You can even keep heating that gas until you get a fourth state, plasma. But what happens if you go the other way? What if you go way down in temperature?
Well, that's when you get this, a Bose Einstein condensate, or a BEC for short. This is the fifth state of matter. It's what happens when you cool a cloud of atoms down to just billionths of a degree above absolute zero. At that ridiculously cold temperature, the atoms stop acting like tiny individual billiard balls. Instead, they start to overlap and kind of lose their identity, merging into a single quantum object. It's like they all become one giant superatom.
To really get a grip on this, let's use an analogy. Think of atoms as members of a marching band. Now, when the atoms are hot, like in a gas, it's total chaos. Band members are just running all over the field randomly. As you cool them down, they slow down. Maybe they're just wandering around a small patch of grass. But when you hit that magic critical temperature for a BEC, it's like a drum major blows the whistle. And suddenly, every single member is marching in the exact same step, perfectly in sync, moving as one unified thing. They're no longer individuals. They are the band. That's a Bose Einstein condensate.
And here's the wild part. This wasn't something that was just stumbled upon in a lab last week. The idea for this fifth state of matter actually came from a prediction made nearly a century ago. It was an idea so far ahead of its time that it would take 70 years of technological progress just to prove it was real.
So to get why this even happens, you need to know a little secret about the universe. Pretty much all particles fall into one of two families. First, you've got fermions. Think of them as the ultimate individualists, like electrons and protons. They live by a strict rule. No two of them can ever be in the exact same state at the same time. But then you have bosons. These are these social butterflies of the particle world. They absolutely love to clump together and have no problem at all sharing the exact same quantum state. And that social behavior, that's the key ingredient here.
So back in 1924, Albert Einstein was looking at the work of an Indian physicist named Satyendra Bose, and he had this incredible realization. He figured that if you could get a group of these social boson particles cold enough, something really strange ought to happen. He predicted they'd all just sort of give up and fall into the lowest possible energy state altogether, condensing not into a liquid but into a single shared quantum state, a superatom. I mean, back then, this was basically science fiction. The technology to get anything that cold was just unimaginable.
And just like that, the race was on. It set the stage for one of the great challenges in modern physics, a 70-year-long quest to reach the coldest temperature in the universe and see if this wild idea was actually true.
Now this didn't happen overnight. The theory just sat there for decades until a huge breakthrough in the 1980s. Scientists figured out how to use lasers to trap atoms and slow them down. It's a process called laser cooling. Then in the 90s, they added another brilliant trick called evaporative cooling. You know how a hot cup of coffee cools down? The fastest, hottest molecules escape as steam, leaving the cooler stuff behind. Well, they did the exact same thing with atoms in a magnetic trap. They selectively kicked out the hottest, fastest-moving ones until what was left was just unbelievably cold.
And how cold is unbelievably cold? Well, the vacuum of deep space is chilly, at about 3 degrees Kelvin above absolute zero. To make a BEC, scientists had to get down to a few hundred nanokelvin. That's not millionths, that's billionths of a degree above absolute zero. A temperature so low it literally does not exist anywhere in the natural universe.
So after all that work, decades of it, pushing the limits of what was possible, it finally happened. In 1995, teams at Gila in Colorado working with rubidium atoms and another team at MIT working with sodium atoms, they both crossed the finish line. They created the fifth state of matter. Just picture it.
You're in the lab. You've cooled this tiny, invisible cloud of atoms to a temperature colder than anywhere in the cosmos. For 70 years, this has only been a prediction on a chalkboard. And now you switch off the magnetic trap holding them in place, you let the cloud expand for a split second, and you take a picture. What do you see?
Okay, so first, when they looked at the atoms just above that magic temperature, they saw exactly what you'd expect from a really cold gas. The atoms were moving at a bunch of different speeds, which shows up on a graph as this broad, shallow hill. This is our marching band again, just wandering around randomly.
But then, the moment they cooled the gas just a tiny bit more, below that critical point, something incredible happened. Right in the middle of that broad hill, this insane, sharp spike just appeared out of nowhere. That right there, that was the smoking gun. It was a huge number of atoms that had suddenly stopped their random dance and were all moving at the exact same, very slow speed. That was the condensate. The superatom was real. Einstein's prediction finally visible. So, okay, they made one. That's incredible. But what does it do? Well, it turns out this quantum cloud isn't just a boring blob. Its shape and its behavior are all dictated by the tiny little forces between the atoms themselves. It all depends on the type of atom use. The forces between them can either be repulsive, meaning they push each other apart, or attractive, where they pull each other together. If the atoms naturally repel each other, the condensate puffs up into a bigger cloud. But if the forces are attractive, the atoms pull on each other and you get a very dense, compact little condensate. And that difference is a really big deal, because those attractive forces come with a serious risk. Yeah, with those attractive atoms, you're walking a tightrope. If you try to cram too many of them into the condensate, their mutual attraction just becomes overwhelming, and the whole superatom can catastrophically collapse. For example, if you're using lithium-7 atoms, that critical number is right around 1400. Add just one more atom, and the entire delicate quantum structure can instantly vanish in a tiny implosion. So you might be thinking, okay, this is a super cool, super cold, fragile little blob, but why should I care? What's the point? Well, this discovery, which won the Nobel Prize, gives us a completely new tool to poke and prod at the fundamental nature of reality itself. A Bose Einstein condensate is like a giant magnifying glass for the quantum world. See, normally, all that weird quantum stuff is hidden away, happening at the tiny scale of single atoms. But a BEC is a quantum object that's big enough to see, sometimes almost a millimeter across. It acts like a single, unified matter wave, which lets scientists directly observe things like superfluidity, the ability to flow with zero friction. And even better, they can be used as perfect quantum simulators to model the extreme physics inside a neutron star or to test our fundamental theories about the universe, all from a lab right here on Earth.
Think about how far we've come, from a wild idea on a piece of paper 70 years ago to literally building a new state of matter, atom by atom. This isn't just some lab curiosity, it's a whole new frontier. And it leaves us with this incredible question. If we can now build quantum matter from the ground up with this kind of precision, what other fundamental secrets of our universe are we about to unlock? Thanks for joining me.